Dear students, in this video we are going to study about the conversion of a galvanometer, which is a moving coil galvanometer, into an ammeter and also a voltmeter. An ammeter which measures the current in a circuit, and the voltmeter which measures the potential difference between any 2 points. Now let us study about the conversion of a galvanometer into ammeter and voltmeter. How we can convert a galvanometer into two devices such as an ammeter and a voltmeter. First of all, let us see what is a galvanometer. It is a very sensitive instrument to detect current. Therefore, it can also be converted into an ammeter as well as a voltmeter. Now let us see how this galvanometer can be converted to an ammeter. Before that, what is an ammeter? An ammeter is an instrument used to measure current flowing in the electrical circuit. And this ammeter must offer a low resistance such that it will not change the current passing through it. So the ammeter is connected in series to measure the current in a circuit. Now, if we want to convert a galvanometer into an ammeter, what shall we do? So you can remember this twice, ALP, where A stands for ammeter and L for low resistance and P for parallel. You can remember the Alps mountain. So a galvanometer is converted into an ammeter by connecting a low resistance in parallel with the galvanometer. And this low resistance is called as shunt resistance S. The scale is now calibrated in ampere. The range of ammeter depends on the values of the shunt resistance used. Now, if I be the current passing through the circuit as shown in the figure, when a current I reaches the junction A, it is divided into two components. So here you are passing a current I, and that current will be divided into two components. One is Ig and the other one is I minus Ig. So Ig is the current passing through the galvanometer of resistance Rg, and that is through the part Age, and the remaining current only, that is I minus Ig, will pass from the part ACDE through the shunt resistance connected in parallel with the galvanometer. So the value of shunt resistance is so adjusted that the current Ig produces full-scale deflection in the galvanometer. The potential difference across the galvanometer is the same as the potential difference across the shunt resistance. Therefore, the voltage across the galvanometer is equal to the voltage across the shunt resistance, which can be written as Ig Rg equal to I minus Ig into S. So we can find the value of the shunt resistance that has to be connected in parallel with the galvanometer, that is given by the expression S is equal to Ig by I minus Ig into R. So the current through the galvanometer Ig is given by S minus S plus Rg into I. Since the deflection in the galvanometer is proportional to the current passing through it, we have theta equal to 1 by G into Ig. Therefore, theta, the deflection produced, is always directly proportional to the current through the galvanometer. Therefore, the reflection produced in the galvanometer is directly proportional to the current. That means the reflection produced in the galvanometer is a measure of current I passing through the circuit. And the shunt resistance R, that is S, is connected in parallel to the galvanometer. Therefore, the resistance of ammeter RA can be determined by computing the effective resistance, which is given by this expression. 1 by R effective equal to 1 by Rg plus 1 by S. Therefore, the effective resistance is given by Rgs by Rg plus S. That's equal to Ra. And since the shunt resistance is a very low resistance and the ratio S by Rg is also small, this means Ra is also small, that is, the resistance offered by the ammeter is very small. When we connect an ammeter in series, the ammeter will not change appreciably the current in the circuit. And for an ideal ammeter, the resistance must be equal to 0. But in reality, the reading in ammeter is always less than the actual current in the circuit. That is, ideal is the current measured by the ideal ammeter, and the actual is the actual current in the circuit. Then the percentage error in measuring a current through an ammeter is given by this expression delta I by I into 100%. That is given by I ideal minus I actual by I ideal into 100%. Now let us see some key points. The first one is an ammeter is a low resistance instrument and it is always connected in series to the circuit. An ideal ammeter has zero resistance. And in order to increase the range of an ammeter n times the value of shunt resistance to be connected in parallel is given by this expression S equal to Rg by n minus 1. Now let us see how a galvanometer is converted into a voltmeter. And before that, let us see what is a voltmeter. A voltmeter is an instrument used to measure potential difference across any 2 points in the electrical circuit. And it should not draw any current from the circuit, otherwise the value of potential difference to be measured will change. And the voltmeter must have high resistance when it is connected in parallel, and it will not draw appreciable current so that it will indicate the true potential difference like this. And a galvanometer is converted into a voltmeter by connecting a high resistance H in series with the galvanometer as shown here. The scale is now calibrated in volt, and the range of the voltmeter depends on the values of the resistance H connected in series. The value of resistance is so adjusted that the current Ig produces full-scale deflection in the galvanometer. And let Rg be the resistance of the galvanometer and Ig is current with which the galvanometer produces full-scale deflection. And since the galvanometer is connected in series with the high resistance, the current in the electrical circuit is the same as the current passing through the galvanometer. So here you can remember this conversion as VHS, where V stands for voltmeter and H for high resistance, and that should be connected in series. Yes. So I is equal to Ig. So Ig is the ratio of the potential difference to the total resistance. And since the galvanometer and high resistance are connected in series, the total resistance or the effective resistance in the circuit is the sum of their resistances. And this gives the resistance of a voltmeter, that is given by Rv equal to Rg plus Rh. Therefore, Ig can be written as V by Rg plus Rh. So the high resistance that has to be connected in series with the galvanometer is given by the expression of H equal to V by Ig minus Rg. And we should note that the galvanometer current is directly proportional to the voltage. And the deflection in the galvanometer is proportional to the current Ig, but the current Ig is proportional to the potential difference. Hence, the deflection in the galvanometer is a measure of potential difference. Since the resistance of a voltmeter is very large, a voltmeter connected in parallel in an electrical circuit will draw least current in the circuit. An ideal voltmeter is one which has infinite resistance. Now let us see what are the key points to be remembered. First one. Voltmeter is a high resistance instrument and it is always connected in parallel with the circuit element across which the potential difference is to be measured. An ideal voltmeter has infinite resistance, and in order to increase the range of voltmeter n times the value of resistance to be connected in series with the galvanometer is given by this expression Rh is equal to n minus 1 into Rg.